In this video, we're going to be talking about the geometry topics of parallel lines, and then we're going to shift a little bit to some objects within circles, talking about central angles and arcs and inscribed angles, and then we'll finish up talking a little about n-sided polygons. So first, when we're talking about parallel lines, let's remind ourselves what we mean by parallel lines. In this graphic here, we have lines L and M are parallel lines. They are two lines that will never intersect. They have the same slope, and you can see that in this case it appears that they are running horizontally, but they can run in any direction, but they will never intersect. So that's for lines L and M. Then we have line T, which here is a transversal. And a transversal is a line that's going to intersect any two other lines. And in this case, it intersects the two parallel lines, and it intersects at two distinct points. So many quadrilaterals and all parallelograms are made up of this structure here of parallel lines and transversals. We're talking about figures like rectangles, rhombi, squares, and trapezoids. Those are the type of figures we're talking about. And as you can see from our graphic here, what we want to do is take a figure and see what parallel lines there are, where the transversal is, and then we know something. We're going to remind ourselves of things we know about the angles and the relationships between the angles in this parallel line and transversal structure, and then we can use that and apply that with all these different figures when we're trying to figure out angle measurements. So if I were to tell you in the figure above that the measure of angle 2 is 73, could you find the measures of the other 7 angles in the figure? Take a few moments and try to do that, and then we'll go over the answers here in just a moment. I gave you that the measure of angle 2 was 73. You can do this in several different orders, but I'm going to help you follow through a process of figuring out these different angle measures that follow. So when we look at angle 2, which we're given, and angle 3, we have a relationship there. Those are vertical angles, and they have the same angle measure. So that makes the measure of angle 3 to be 73 as well. Now let's take a look at measure of angle 4. It has a supplementary angle relationship with angle 2, and it also has one with angle 3. But let's go along with using angle 2, because that is the angle that we were given. Supplementary means that when you add up the two angles, or add up any of the angles that have a supplementary relationship, it equals 180. So we can take 180, subtract 73 from that, because that's the measure of angle 2, and we get that the measure of angle 4 is 107. Then, in turn, we can use that angle 4 and angle 1 are vertical angles, so the measure of angle 1 is the same, it's 107. Now we're going to look at the angles at the bottom. We know that angle 2 and angle 6 are corresponding angles. For the ACT, you don't have to remember the name, but you need to remember the relationship. The corresponding angles, when you have two parallel lines cut by a transversal, corresponding angles I think of are almost the angles we skip. So 2, skip 4, and we go to 6. So 2 and 6 are corresponding. That means they're the same angle measure. So angle 6 is equal to 73, the same as angle 2. Now we can shift to our vertical angle relationships now that we know what this bottom portion is going to kind of look like. Angle 6 and angle 7 are vertical angles. They're the same. So that makes angle 7, 73 degrees. We can look at number 8 through this supplementary relationship. Here we use that angle 7 and angle 8 are supplementary. So we took the 180 minus the 73. That gives us 107 degrees for angle 8. And that just leaves us angle 5, which has a vertical relationship with angle 8, making angle 5 107 degrees. So all 8 of these angles either are 73 degrees or 107, all based on the different relationships that we're given. There are several other ways that you can solve for this. We know a couple of things. We used corresponding angles and vertical angles, but if you remember some of your terms from geometry, we have same side interior angles, alternate exterior angles. Again, on the ACT, I've rarely ever seen those terms used. I have seen supplementary before, but you have to know the relationships. When I said same side interior, we can look at angles 4 and 6. They add up to 180. 3 and 5 add up to 180. Alternate exterior angles, such as 1 and 8 or 2 and 7, those are the same. They have the same measure. So be familiar with all these angle relationships that come from geometry. And remember, you can apply these relationships with different figures as you're trying to figure out angles. If you can break it down into two parallel lines, cut by a transversal, and remember these relationships. Now let's talk a little bit about central angles, and we find these within a circle. By definition, a central angle is an angle whose vertex or center is at the center of a circle. And we see that in the figure above, the central angle given by x. So the legs of the angle are the radii that intersect the circle at two distinct points. And we have labeled here A and B. We have the line OA, which is one leg of the angle, and then the leg OB. That forms the angle, this central angle. Looking at the portion of the circle circumference, remember circumference goes all the way around a circle. Looking at the portion between A and B, that is called an arc. We have the arc AB, and we really have two arcs. We have the arc AB that is marked, as you can see, by the 80 degrees. And then you can also think of an arc that's the bigger portion going clockwise from A to B. When we need to know something about the length of the arc, we're going to make use of the circle circumference a lot of times, and we'll look at that here in just a moment. So one measurement that we could be asked for is the degree measure of the arc, and that is equal to the measure of the central angle that intercepts the arc. So in our case here, we know that if we're looking for the measure of the central angle, it's the same as this degree measure of the arc. And we're labeled here that the degree measure of the arc AB is 80 degrees. So that's going to make the measure of the central angle also 80 degrees. They are the same. Now when we're talking about an arc length, we're talking about the length between A and B in this case. And this is a proportion of the total circle's circumference. We kind of referred to that a few moments ago. If we want to find the arc length between A and B, we're talking about their A to B going counterclockwise. This arc length is going to be the proportion of the central angle divided by 360. So we're looking for the measure of the central angle divided by 360. We use 360 degrees because that's the total measure of a circle. That is a proportion, that is a fractional portion. We're going to multiply that by the total circumference of the circle, and that will give us this arc length. It's a proportion of the total circumference around the circle. And that's what we're saying right here, that we are looking for a fraction of the total circle times the circumference. That's going to give us that arc length. Now when we're looking at this sector of this arc, this proportion, we're talking about almost this pie piece. When we were talking about arc length, we were looking more at circumference. Here with sector, if we're looking at this total sector, we're going to be looking more at area. So the sector is the area enclosed by the two radii and an arc. Like I said, a lot of times we may say a pie piece. When we're talking about sector here, we're talking more about area as opposed to the arc length. We were talking about circumference. For the sector's area, we're going to take a fraction of the full circle's area. Remember, the circle's area is pi r squared, and we'll just take a proportion of that. So we have the full circle, and we're going to take one sector. We're just looking at a proportion of that. So again, we're going to do some multiplication of the central angle divided by 360. That gives us our fractional proportion, fractional area, times our area. So that gives us the area of the sector. Now we're going to look at inscribed angles. We're still using a circle inside a circle. And an inscribed angle is formed by two chords in a circle which have a common endpoint, the vertex. So in our case here, our graph that we're given, the vertex is at B, and we have those two chords that are drawn in red. They're going to go from one point on the circle to another point on the circle. Now the other 2 points, A and C, form an intercepted arc, and we see that here in our picture. We're given the measure of the arc in our picture above as 100 degrees, and there is a relationship between the measure of the inscribed angle, which is X in our picture. It is half the measure of the arc, or half the measure of the corresponding central angle. If we showed the central angle that was formed by AOC above, that is the same as 100 degrees. And now we're going to look at what is the measure of X, which is the measure of the inscribed angle. It is half of that arc measure, which would make it half of 100, which is 50. So the two main angle measures we want to look at, the central angle is the same as the arc measure. The measure of the inscribed angle is half of those two. Now another thing about angles and circles, let's just do a reminder here. If we look at line L, we say that it is tangent to the circle at point T. Now this word tangent here is a different use of when we're talking about it in a trigonometric function as sine, cosine, and tangent. Here, line L is tangent means that this line touches this circle at one point, and it is at the point T. So if I asked you, what's the name, if we drew a line from point C, the center of the circle, to T, what would we call that line with respect to a circle? That is the circle's radius. We know from point C to T is a radius. Now, the measure of the angle formed by the line from point C to T and line L, what would be the measure of that angle? It is 90 degrees between the radius and line L. And we go over this because sometimes we'll be given this information like the figure above, and you may be asked for some other angle, but knowing that you have a 90-degree angle when you draw a radius, that could help you. Again, this is information we're putting in our tool belt, and we use it as we need to as we're looking at these different figures. What do we call the longest chord? And it divides the circle into two semicircles. The diameter. So remember, we talked about a chord when we were talking about inscribed angles. The longest chord is a diameter. It runs through the center of the circle. Our final topic in this area, we're going to talk about n-sided polygons. So n represents how many sides are on that polygon. So when we're talking about something like a rectangle, we know it's a four-sided figure. N is 4 in that case. We're usually familiar with triangles, rectangles, maybe even pentagons, a 5-sided figure. But as we get on up, like with a 10-sided figure, 12-sided figure, that sort of thing, we may not know the actual names for that, but if we're given 10-sided figure, you know that n is 10. We can figure out a lot of different things that we might need to know about angles and even side lengths. So here is a handy formula. You need to know this one because it can come into use, that the sum of the angles of an n-sided polygon is n minus 2 times 180. So we're talking about any n-sided figure, polygon, closed figure. We could add up all the angles inside that polygon, and we can use this formula to determine what that measure should be. So for example, a lot of you should be familiar that the angles in a rectangle sum up to 360, the 4 angles. We're able to use this formula actually to get that. Most of us, we just know that. We remember the 360. But let's take a look at the use of the formula so that if you can remember the 360, you can always get back to this formula if you remember a few things about it. So we plug in 4 for n, that's the number of sides. 4 minus 2 is 2 times 180. That gives us the 360. So it's easy to remember we know for triangles it's 180, 360 for a quadrilateral. And beyond that, you may not have it memorized, but if you'll take this formula, you can use it and apply it. So talking about a pentagon, if we have a regular pentagon, remember what regular means. That means all of the angle measures are the same, so all the side lengths are going to be the same. So for a regular pentagon, the sum of the interior angles is what? First of all, we're going to apply our formula. N is 5, so we have 5 minus 2 is 3 times 180. That gives us 540 degrees for a pentagon. So if we were asked to find what each interior angle measure is, since it is regular, we can take the 540, divide it by the 5, and we get 108. Now we can only do that because we know it's regular. There are several different applications of the use of this formula. You may be given, example, in a pentagon, maybe you're given 4 of the angle measures and you're asked to find the 5th one. Well, knowing that it's 540, you can subtract the ones you're given and you can find the 5th one. So that's a common question that we see. But make use of this and just again remember it, and as you need to apply that knowledge, you'll be able to do that. So let's take a look at an ACT type question. Pause the video here and work this question, and then come back and we'll work it together. You're told that in the figure below, line L is parallel to line M. You have transversals V and W that intersect at point A on L and intersect M at points C and B, respectively. Point Y is on M. The measure of angle ACY is 125, and the measure of angle BAC is 70. How many angles formed by rays of L, M, and V and W have measure 55? Sometimes it's a little easier if they ask us, what is the measure of angle A or the measure of angle B or whatever it may be. In this case, we've got to look at all of our angles. So we're looking for those that have the measure of 55. So when I'm looking at this, I've given the 125 and the 70, and we're going to have to use a couple of relationships. And when I look at 125, I know that anything that's supplementary to that is going to be 180 minus 125, which is 55. And so that's going to give me these angle measures right here, any in the red. That gives us these. We have some vertical angle relationships. We know that because of the vertical angles, we know that things are going to be divided up and equal to the 55. And that turns out to be, there are 8 angles with a measure of 55 degrees, as we see here labeled in red, colored in red, and that is answer choice C.